transmission and distribution wires move energy through space, whereas batteries move energy through time. The homes that are just around here, that normally get their power from that plant, now have to import it from upstate. There are big transmission lines, but it turns out not enough capacity to move that power from where it's generated to where it is consumed. The big challenge that batteries solve generally is flattening out this curve.
Here for you, LMP, even though it's a price and it's an economic variable, you're using it as a sensor, basically, like a grid sensor.
The more fine-grained you are in your nodes, so if a node measures a substation at a neighborhood, what if you had a node at every home?
Welcome to episode 2. Today we're here with Justin Lopez, COO and co-founder of Base Power, and he's going to tell us how the grid actually works. I think Base is one of the most interesting companies being built right now. They're basically building a distributed power grid, a network of batteries on people's homes that provide an alternative energy source when the grid is low on power. You can imagine grids have this huge peak-trough problem where the demand at peak is very different to the demand at the trough. And with AI workloads coming online, that's going to get even more spiky. Base is reimagining what a utility company looks like and making it entirely distributed. We couldn't think of anybody better than Justin to give this lecture. He's previously built incredible hardware as an engineer at SpaceX and at Anduril, and we're really excited to give him the chalk today.
So this is transmission, this is distribution, and this is generation. In most countries, but not all, the grid operates on 60 hertz. And that means that it switches from positive to negative 60 times per second. It operates on what's called alternating current, and alternating current is exactly what it sounds like. It alternates from positive to negative. So if you look at a sort of waveform of the grid, you'll see that it looks like this. It's a sine wave, and the switching happens 60 times per second. In some countries, it's 50. In Japan, as an example, it's 50 hertz system. For typical old school, quote unquote, power generation, so not solar or wind or batteries, but if you look at coal, nuclear, and natural gas, there's literally a spinning disk inside of the turbine, right? So whether it's nuclear, which drives heat, which makes steam, which then drives a turbine, or it's natural gas that is directly powering a turbine, this turbine is spinning at a certain rate. And that rate needs to stay constant with the other power plants, I should say consistent with the other power plants on the grid as well, right? Not only does it need to be spinning at the same speed, but they also need to be phase matched. So, you can't have one natural gas plant that looks like this, and then the next natural gas plant that looks like, say, this, right? That would not be good. You want them all to be in sync, in phase with each other. So they'll if you imagine there's like a little dial here, the dials are all at the same point for all of the synchronous generators, as it's called, because they're synchronized to each other. And the 60 hertz number is very important because as you add more load here, you add more homes or people turn on their ACs or whatever, you can imagine almost like it puts more load on these generators, and so they want to slow down a bit. And so how close you are to 60 hertz on the grid is very, very closely monitored for how much load there is on the grid. Similarly, let's say you have a bunch of homes, or you have a big data center here, and it's using 500 megawatts of power, and then all of a sudden, for whatever reason, it trips offline. Now these generators are going to spin too fast, and so you're going to go too high on your frequency. And so the grid operators, which we'll talk about in a minute, are watching this number extremely closely. It's like a few tenths of a hertz above and below 60. There's like big problems on the grid. There are oftentimes switchgear inside of substations that will automatically disconnect themselves to avoid damage to the loads on their that they're plugged into. If you go, say below, and again, this isn't exactly the correct numbers, but say 59.5 or 60 or above 60.5. So this is very tightly controlled. And the way the grid operator is thinking about this is they're like, okay, big data center plugged in, we need more generation over here to make sure that we're able to keep up, basically, with that 60 hertz. This whole system is monitored by the grid operator. In most parts of the US, you have what's called an ISO, an independent system operator. Independent system operator. You'll hear these referred to as RTOs, stands for regional transmission operator. For the purposes of this discussion, these two things are the same. And these are collectively the grid operator. Okay, so these guys are charged with monitoring the whole system. They don't own transmission, they don't own generation, they don't own substations or distribution, and they don't sell power, but they're responsible for making sure basically that these numbers don't go too far out of bounds, that there's enough generation to meet the load, and also they're controlling the financial layer on top of this, which we're going to spend a lot of time talking about here next. So there are a number of ISOs/RTOs here in the US. In Texas, the major one that covers most of the state is called ERCOT. So ERCOT stands for Electric Reliability Council of Texas. And they are the ISO that controls about 90% of the load, 85 to 90% of the load in Texas. They don't own transmission or substations or distribution. They don't sell power. You don't, as a retail customer, you don't engage with ERCOT in any meaningful way. But they're responsible for making sure all of this coordination happens. So you can think about them as sort of the air traffic control, as well as the New York Stock Exchange of Texas electricity. Let's say that Texas is a square state, just so I don't have to draw the whole thing. So in Texas, there are, inside of the ERCOT boundary and specifically, there's these things called nodes. And nodes are what you think they sound like. They are basically typically substations or generation locations on the grid. And so they're typically, you have a substation node, and then there's like a bunch of feeders to homes outside of those nodes. But these nodes are connected to each other through transmission. You get the point, right? And so each one of these nodes is on the transmission system. And then if they are substation nodes, they have radial feeders that feed to homes and businesses, okay? And what ERCOT does is they measure the power flows on these transmission lines that run between nodes. And they calculate every 5 minutes in Texas, like a stock, the price of the electricity that is consumed at that node. So if you're a consumer or a producer of power at that node, you either get paid or pay what's called the LMP. So LMP stands for locational marginal price.
So when they're measuring the power transmission,
yeah,
is this like a enhanced version of like a big multimeter on a wire, or what is it? How do they do that?
Yeah, so if it's at a substation, they'll typically have what's called a current transformer, which is like basically a coil that is like hovers around a wire, and it measures the magnetism that is induced as current flows through that wire, and therefore you can calculate the amount of power that is going through that wire. Yeah, you know what there's a tap for voltage, and then this gives you current. This is the current transformer, and this is like just a sensor on the wire that gives you voltage and current can give you power. So ERCOT, in this case of Texas, they calculate the LMP at every node in the grid every 5 minutes. So what's important to know is that the price is dependent on basically two things. It's basically a function of the supply and demand at any given point. So you have the price of energy at that node plus the cost of congestion, which I'll explain in a minute. Plus losses, but the losses is a small component. Every 5 minutes, for thousands of nodes on the grid, ERCOT publishes a price. And if you are let's say this is a node in Dallas, and you're a commercial customer that is plugged into that substation. You're on the distribution line plugged into that substation over here. You pay generally the LMP at that time, or the retailer that serves you, which I'll explain in a minute. So the locational marginal price, the way to think about this is the marginal kilowatt of power supplied or consumed at that node is what sets the price. It's the marginal producer or the marginal consumer. And so this price is calculated all the time. And if there is an area where you have a lot of congestion, you have high prices typically. So, for instance, let's say you have in South Texas over here, you have a natural gas plant. This is a big power generator. And that natural gas plant, for whatever reason, trips offline. There's an issue, a maintenance problem, whatever. It trips offline. The homes that are just around here that normally get their power from that plant now have to import it from upstate. They have to import it from San Antonio or Austin or Corpus Christi, right? And so now, instead of power flowing a very short distance from that generator to the load, you now have to have it flow a long distance, and all of the homes around that are now trying to get their power from San Antonio. And so there ends up being congestion on that line to go to that substation. And so then the congestion portion of the LMP equation goes up, and therefore now that home or that business is paying more for their electricity in that moment.
Oh, interesting. So if you have like online generation nearby you, your congestion is typically lower and your price is better, or is that the wrong conclusion?
That's a good heuristic.
Okay.
There's obviously a bunch of complicating factors. It's basically like the way to think about the LMP is it's basically a function of supply and demand at a given time. One key thing I haven't mentioned yet that I think is really sort of worth always having in your head when you're thinking about the grid is all of your measurements are at a point in time, right? The grid is a very dynamic system. It changes throughout the day, meaning some of your generators are solar panels, right? And we'll talk about this more later, but that solar is producing a ton along that transmission line or into that node, at 12 p.m., but then at 12 a.m. it's producing nothing. And so now that line is totally unused, and those homes nearby need to import their power from somewhere else, as an example. So the interconnectedness of the grid is very important. And if you have a bunch of load in one location and a bunch of generation in another, but a weak transmission system or a small line between them, you end up having a bunch of congestion. So taking the Texas example, this is just a general example that's pretty repeatable, is you have a lot of solar in the western part of the state. You guys fly in from California, if you fly over West Texas, you see a bunch of solar and a good bit of wind, but nobody lives there. So you got to get all that power to where it's used, which is Houston, Dallas, Austin, and San Antonio, right? And so there are big transmission lines, but it turns out not enough capacity to move that power from where it's generated to where it is consumed. And so you often have congestion on the east to west lines. You have congestion going, one direction during the day and then in the other direction at night. And so the grid operator is also driving an incentive structure for people to build out generation to their load or to other load on the grid, and also incentivize transmission build out. You can think of a developer or an owner of power plants or batteries like us as sort of chasing the incentive, so to speak. So if there's a bunch of stranded generation, like there's a bunch of solar in West Texas, but there's no one around there to consume all of it, and it can't get to market, it can't go east to the people where the people are consuming it, then it is great for someone to soak up that excess energy and then distribute it more slowly overnight, which is what batteries do, as an example. Okay, so we talked about locational marginal price, how ERCOT sets it, ERCOT being an ISO, and sort of overseeing this whole thing, and being very, very focused on how do you keep supply and demand balanced, not only overall in total, if you add up all the generators and you add up all the load, those two things need to be equivalent at any given time, but also locationally, right? It not only matters that you have the total amount of generation to support the total amount of load, but that you have it in the right spots. And and you also have it at the right times, right? It's a geography and a temporal issue, as well as a sort of bulk system issue.
So you care about power as a function of space-time, actually.
Exactly, you do. That's right. That's right. So now I think it's important to talk about how batteries play in all of this. So as I mentioned, you have both geographic effects of price and power, as well as time effects of price and power. The way you can think about it is transmission and distribution wires move energy through space, whereas batteries move energy through time. So at any given moment, ERCOT is charged with making sure there's at least enough generation to support that load. it's like having a water system, but if you don't have batteries on that system, it's like having a water system with no tanks. It means that you would have to, pump out of a well at the exact rate that you're consuming in your shower. And there's no sort of like storage in the middle. And so this is where batteries come in, is they allow you to have mismatched supply and demand, like instantaneous generated supply at the moment and demand, which is great because in general, the average utilization of the grid is on the order of 50%. But during peak times, it is at or can unfortunately be over 100%. So what's important to note here is that if you look at throughout a given day, let's say that this is time and this is load, like total aggregate load on the grid. Typically, especially in like the winter in Texas, you have like, a little bit of a morning peak, then a bit of a dip, and then you have a big evening peak, and then you have another dip. And this is like not a whole lot more complicated than people are asleep here, and people wake up here and they cook their breakfast, then they go to work, and then they come home and they like charge their EV and cook their dinner. This is generally load, and the reason also why you have two peaks in the winter is because oftentimes you have heating load that drives a lot of your demand. In the summer, it typically looks more like this. In Texas, you have really, really high peaks in the evening because you have a bunch of heat and like solar radiation into your home that heats up your home, and your cooling load spikes later on in the day. Your cooling load actually spikes as the temperature outside is cooling off because a bunch of the heat is absorbed into your house. Anyways, the point being, the grid has to support this load. Not only this load in any given day, but the highest load that you expect over the next few years until you build out more transmission and distribution infrastructure. But the rest of the time, all of that capacity is underutilized, right? All of that, right? So if you built out enough generation to match this instantaneously at this moment, that generation would need to be turned off during these times because there's nowhere for it to go.
Just with, obviously AI data centers coming online, do you see sort of a future where like user querying or querying that's driving inference changes the shape of that curve?
The general idea still applies that like inference that is like person types into, ChatGPT a query and then that query results in an answer is like a synchronous use of inference, which is sort of the same phenomenon. It's like when you're awake, you're not querying when you're not awake. Now there are inference jobs that can run overnight, and there's also interesting data center architectures, again, I don't profess to be an expert on, where during peak times you're doing synchronous work and you're doing asynchronous work to sort of flatten out this curve, so to speak. The big challenge that batteries solve generally is flattening out this curve, right? So you have a bunch of unused capacity here just so that you can make sure that you deliver it up here, right? An unacceptable outcome for the US grid is that it's like, well, too many people are using electricity. Sorry, you can't turn on your lights now, right? That doesn't work. The R in ERCOT does not allow for that. It's the reliability part, right? And so batteries help smooth this out. So what batteries can do is they can discharge during these windows, flattening out that peak, basically effectively lowering that peak load, and they can charge during these trough times. There's an interesting concept here called net load. It is basically total load on the grid minus renewables. So here in Texas, there are a handful of major components to the generation stack, those that are generating power. You've got, in their order for the most part, you've got gas, you have solar, you have nuclear. There are two major nuclear plants in Texas. You have wind. Actually, wind is above nuclear in terms of its size. And then you have coal, and you have batteries. And if people are curious about this, you go to ERCOT.com/dashboards. You can see at any one time what the makeup of these are. And what you'll find, especially when it's sunny out and there's not a ton of load, it's like today, it's 50 or 60 degrees. You have a large component, sometimes over 50%, that is supplied by solar in the middle of the day. It's pretty wild. Texas is the leader in solar. And that's great. But the challenge is that, that 50% of the generation goes away in the span of a few hours as the sun sets. And so that's where batteries come in. So batteries can store the excess solar, either that's generated in an area where there's not a lot of transmission capacity to sell it immediately to market, or just in general, you can, store it from rooftop solar and then discharge it overnight when there is no solar. The way to think about it is, if you have your total load here, like that, that's a typical load shape for a given Texas day, maybe a winter day because you've got this morning peak. Your solar is around for about, say, here. So these are the solar hours. But over here, there's like zero solar. And obviously, there's like a shape to the solar, right? Solar falls pretty quickly and rises pretty quickly. But so the challenge that batteries can, or the challenge that batteries can solve is they can soak up this excess solar here, and then they can discharge it overnight. That's what batteries do in bulk. Now, our systems at Base Power, we do a distributed battery. So there are two major categories of batteries. There are centralized batteries. You can think of a centralized battery, visualize it like a shipping container stuck on some farmland in the middle of nowhere in Texas. If you fly from Austin to somewhere in California, if you look very carefully, there'll be a big solar farm, and then right next to it, oftentimes, there's like a bunch of shipping containers sitting there. Those are batteries. And so those batteries help the bulk transmission system. They're connected into the transmission lines here, or they're attached directly to the solar farm here, right? What we do is we slide those batteries all the way to the end of the grid, and we attach them to the home. And we do that in thousands, almost in tens of thousands of places throughout the grid. So instead of having one big battery right here, and we're only able to affect the power flows on the network or on the grid that are right nearby it and sort of affect it in a bulk sense, we're also able to affect the power flows in a distributed sense. So we can say there's a neighborhood in Dallas that needs more power now, and so we'll discharge that. That LMP is high, so we're incentivized to discharge. But over in West Texas, it's still sunny over there, and so we're actually going to charge because those LMPs are negative or zero. It might be free for us to be charging batteries.
So you can do much more precise, localized adjustments, basically. You're like
Exactly.
fine adjust for...
Exactly. So the way to think about it is every node has many batteries on it. Right? These are my little squares here are our batteries. And so we're able to adjust the power flows on the distribution grid and upstream of that on the transmission grid by virtue of controlling our batteries. Sometimes batteries in distributed sense are called virtual transmission, right? The concept being instead of having a big transmission line running from Dallas to Houston, you can, excess power from Dallas being shared down to Houston, so power is flowing from north to south. You can instead charge your batteries in Dallas and discharge them in Houston, thereby offsetting that demand and supply imbalance between those two cities without having a really big, expensive transmission line running through it.
And one more question, when you showed the solar chart and you talked about the net load,
Yeah.
I mean, is it fair to think that in the limit, batteries should equal renewables to compensate for all fluctuations?
Yes. In the limit, if it's just solar and let's say there's no wind for a second, because wind and solar oftentimes actually are offset from each other. It's windier at night than it is in the heat of the day. If you have 100% solar, then you need just as much battery to compensate for that solar, basically. And you charge on the excess solar during the day. Solar supplies some of the load, and then the rest of it goes to charging the batteries. And then at night, you're discharging the batteries, and the whole grid is supported by batteries. We are a participant in that, and we're able to store excess electricity from local power plants and rooftop solar, and we're able to push it back into the grid or offset the load of the home to take that home off of the grid during peak times here so that the actual demand curve gets flattened.
And so here for you, LMP, even though it's a price and it's an economic variable, you're using it as a sensor, basically, like a grid sensor.
Exactly. LMP is a signal to us for what we should do with our systems.
You mentioned that ERCOT updates it every 5 minutes. So you sort of see this evolving. Do you think that is something that would have to change in the future?
Generally, yes. The more fine-grained you are in your nodes, so if a node measures a substation at a neighborhood, what if you had a node at every home? right? Then you can balance the distribution grid power flows, not just the transmission grid power flows. So generally, the more frequent the measurement and the more tightly spaced geographically the measurement is, the more accurate or the less headroom you need on your system to have excess demand or supply.
Earlier, you talked about the data centers creating more load and some of that. If you read the news in terms of just how many gigawatts they seem to be building for a specific data center, would it be reasonable to assume every data center also needs like a battery? They need like a local small version of this entire grid, like a small fractal grid, or?
Yeah, this is maybe stating the obvious, an extremely hot button political and economic and sort of grid policy issue right now. So we could spend a whole hour on just this particular topic. The short answer is yes. Data centers having both generation and storage co-located with them is a great feature for them to have. In the same reason why homes having batteries on them is also a great feature, because you're able to offset the load during peak times and flatten, that same peak curve without needing to tap into the distribution or transmission grid where you have to like move the power from one place to another. You can do it all on site. The challenge with that is space, is permitting, it's the supply chain of natural gas turbines, because that's going to be the fastest thing to build. Batteries, in particular, though, play a great role because the power fluctuations, basically how much energy a data center is using at any one time, changes very, very rapidly. This is different than a home, which has your AC comes on, your AC goes off, you turn on some lights, but it's not very, very spiky within the span of less than a second. And so batteries do a lot of power conditioning or power quality work on site with data centers today.
And then, we obviously are most familiar with lithium-ion batteries, because you think about, is that still kind of what's prevalent? Is that changing in the future?
Hot topic is what the next chemistry is. Many believe I believe it is sodium ion will be the next chemistry, but
why do you think the future is sodium?
The raw materials are just way, way cheaper. So sodium versus lithium carbonate prices, sodium is if memory serves, 1/100th the cost on a per unit basis. And there's been a lot of commercialization work done on sodium. It's sort of like everyone converged around LFP because it was actually invented down the street here at UT Austin. And it turned out it was the best chemistry, and also just a bunch of companies ended up building a bunch of scale and therefore driving down the price. And we're seeing the same thing in the sodium market. A lot of the Chinese companies are investing pretty heavily in sodium ion chemistry. But today, right now, if you look at all the batteries on the grid, they're one of these two flavors, and almost any new battery is all LFP.
Justin, thanks so much. That was awesome. Really appreciate the time. This was fantastic.